Hello, this is Mingrui Zhang from Tsinghua University. Today, I would like to introduce our innovative automatic fast driver synthesis framework, IntelliGen. To start our introduction, I would like to first introduce the pipeline of traditional fuzzing. Fuzzing is a technique widely used in vulnerability detection. To fuzz a library, we need to write a program manually that calls interesting functions defined in the library. Then, we run the program by the Fuzz engine with randomly generated seeds. It can help us trigger the bugs in the library. However, writing an effective Fuzz driver can usually be extremely labor-intensive. Therefore, it is necessary to generate the Fuzz driver automatically. To generate a Fuzz driver automatically, we must solve the two main challenges. The first one is to determine which function to fuzz, and the second one is how to call the target function correctly. To overcome these two challenges, here comes the IntelliGen framework. This is the IntelliGen framework workflow. It contains two main components, entry function locator and fuzz driver synthesizer. IntelliGen takes the target library as its input. First, it finds the interesting functions by entry function locator. Then, it runs fuzz driver synthesizer to generate the LLVM further test one input function, which calls the interesting function found by entry function locator. Finally, we compile the synthesized function LLVM further test one input and link it with the target library to get an executable program. This program is the automatically generated fuzz driver. Now, let's see how IntelliGen works step by step. First, I will show you how entry function locator works. IntelliGen provides entry function locator to find potential function to fuzz. Specifically, entry function locator scans the target library, finds functions defined in it, and calculates their priority. In the later fuzz driver synthesizing step, we will generate fuzz drivers in the order of the function's priority. Three kinds of operations can increase the priority, including dereferencing a pointer, calling a memory-related function, and calling other functions defined in the target library. Here is an example to illustrate how the entry function locator works. Here, we would like to get function A's priority. At the beginning, all functions' priority is set to 0 by default. Then, we find that function A calls function B and function C inside it. So, we add function B and C's priority value to function A. Next, we increase function A's priority by 1, since it calls memset, a memory-related function. Moving on, the function A dereferences a pointer twice, so we add 2 to function A's priority. Finally, we can get the priority of all functions defined in the target library by repeating the above process. After getting all functions' priority, IntelliGen will synthesize fuzz drivers in the order of their priority. Let's move on to fuzz driver synthesizer. IntelliGen guesses the full value of the argument inside the function that is going to fuzz by fuzz driver synthesizer. More specifically, fuzz driver synthesizer instruments the target library to delay the assignment of the values referenced by a pointer until it is first used. This process, we call it lazy store. To lazy store inside the pointer, IntelliGen first checks if the pointer has been stored before. If the pointer has been stored by the program or by IntelliGen, then nothing happens. Otherwise, IntelliGen checks the type that the pointer points to. If it points to a scalar type, IntelliGen reads same length of bytes from the fuzz engine and copies them to the address of the pointer. Or else, IntelliGen allocates a large buffer and marks the buffer as unstored, then assigns the beginning of the buffer to the pointer. With the instrumented library, we can pass a raw pointer to a pointer type argument of the entry function to fuzz without filling in it. In this way, we can easily build the fuzzer's interface function LLVM further test one input. Here is an illustration on how we instrument the library. Suppose that we are calling function B. When getting the variable cc, IntelliGen first checks whether cc has been stored before. If not, IntelliGen reads 1 byte from the Fuzz engine and stores it to the address of the variable cc before the dereferencing operation. As for the pointer type variable in the pointer, if it has not been stored before, IntelliGen allocates a large buffer and marks the buffer as unstored. Then, IntelliGen assigns the beginning of the buffer to the variable in the pointer. In addition, after the lazy store operation, IntelliGen marks the variable as stored, in order to avoid twice store. After implementing the 2 components, we evaluate the IntelliGen framework on some industrial projects, and here is the result. We use the Fuzz driver given by Fuchen on GitHub, and our synthesized Fuzz drivers. Run them for 24 hours and choose the driver with the highest coverage as the result. On projects like AVC and like HEVC, IntelliGen covers nearly twice as many basic blocks as Fuchen, and on projects like MPEG2, IntelliGen covers a lot more basic blocks than Fuchen. On library like GSM, IntelliGen covers almost the same number of basic blocks with just a half number of paths than Fuchen does. And here is a growth trend for basic blocks and paths. To conclude, IntelliGen is a framework to generate Fuzz drivers automatically by finding interesting functions in the library and synthesizing Fuzz drivers according to the interesting entry functions. It covers 203% more basic blocks and 136% more paths than the state-of-the-art Fuzz driver synthesis framework, Fuchen. To make IntelliGen more mature, our future work includes synthesizing Fuzz drivers with more domain knowledge and finding a smarter algorithm to locate entry functions. Thank you. Any questions?
Make the
Good morning, everyone. Welcome to this session titled Testing Automation. I have the pleasure to be your session chair today. My name is Jose Rojas, and I work at the University of Leicester. I have the pleasure to have Mingrui Zhang from the University of Tsinghua here with me. It is his first conference paper, so let's be supportive to him and let's be welcoming to him in ICSI. And yes, please, if you have questions, start posting them on the chat channel. Mingrui, very nice work, I have to say. Thank you very much for the work and thanks for preparing that presentation. I have the first question, perhaps, while people start posting theirs. What is the reason behind choosing the 3 operators that you choose to calculate priorities for your functions? You know you use pointer dereference, memory-related functions, and function calls. Why did you choose only those 3 elements?
Because these 3 elements may cause the memory volunteers these 3 elements may cause memory related vulnerability, such as heap buffer overflow or use after free. And to meet some deep functions, we need to call the top level functions to try to get the deepest function, and by calling the first level function, we can find much paths and branches other than call a lower function. So I choose the one element is the so I choose one element as the calling other functions in this project.
Could you perhaps also use other metrics, like, for example, the size of the method or the cyclomatic complexity of the method to assign priorities?
The complexity of the algorithm is about O(n), And because first of all I will scan the project and find functions that has all the calculate the priority for all functions according to the 3 elements. And when meeting a dereference operation or calling a memory-related functions or calling another functions in this project, and the priority of the function will be increased. So after scanning the project, I can get all the priorities of the functions. And I have tried my project on some real project in Google Further Test Suite.
It's practical.
And it is practical.
Yes. Yes. So can I ask you something about your results now? Yes?
Yeah.
In your results, you have one particular subject that is libGSM, where the results seem to be better for FuzzGen. So FuzzGen seem to outperform IntelliGen.
Yes, LabGSM is a strange project, but we have tried to improve its performance, but IntelliGen at that moment IntelliGen can't perform better than FuzzGen, and we have tried to improve our performance after the paper have published, and current IntelliGen can cover a little more branch. It can cover a little more basic blocks than FuzzGen, but current it can cover a little more basic blocks, but not the time when the paper published. So I write the data when the so I just get the basic block coverage on when the paper has published.
Okay. So in your results, you explain very well that your IntelliGen approach is better in terms of coverage, right? So you cover more code than FuzzGen in general. However, I didn't see any results or discussions on the number of crashes or the number of bugs that IntelliGen can find. Do you have any results related to number of bugs that you can find?
Currently, the IntelliGen may detect some wrong bugs on the fuzzing, and wrong bug. We are trying to decrease the false positive rating. We have found the bug in the LabChar ML in Google's Further Test Suite, but LabXML in Google's Further Test Suite. But currently we have the false positive rate is higher. It is rather high, and so I'm trying to
decrease.
I'm trying to decrease it. Yes. The bugs detected by IntelliGen is it is selected by ourselves. We have 我们确保它是真实的 bug. We have determined that it is a real bug we have found. On this pipeline, we have checked about about 100 or 100 to 1,000 trace files, and there are many false positives. So we have improved IntelliGen these days, and its false positive rate is lower than the paper published time.
I see. So I understand then that number of false positives is one of the limitations of IntelliGen at the moment.
Yes.
You are working on it. I understand that. Very quickly, because we only have 1 minute left for the Q&A, could you discuss other limitations that you observe in your approach?
就是你还有没有别的 limitation？
Except that false positive, you have some limitation on the function pointer's location. If a function takes a function pointer as its argument, then IntelliGen cannot assign the correct value for the function pointers at the moment. But we have solved this problem. We have solved this problem in these years. And maybe in the next paper we will describe how to assign the values for the function pointers on generating fast drivers automatically.
Thank you very much, Mingrui. Very nice work, very nice presentation, and congratulations on your first ICSI paper.
Okay, thank you.
Thank you to the audience for attending this Q&A. Our next paper is titled Layout and Image Recognition Driving Cross-Platform Automated Mobile Testing. I'll see you in 10 minutes for the Q&A.